We have 16 participants for now. We can wait 2 minutes and then we start. I think we can start. Let me share my screen. Okay. Hi, everyone. Welcome to this new episode of the webinar series organized with by ISPRS Student Consortium and ISPRS. Today, we're going to have Professor Jan Wegner from University of Zurich and ETH Zurich talking about deep ensembles for global vegetation analysis. First, a few words about ISPRS Student Consortium. We are the official representation of the youth of to ISPRS, the International Society of Photogrammetry and Remote Sensing. We aim to link students, to bring students together from all over the world and young researchers that share the same passion to our discipline, which is photogrammetry, remote sensing, geoinformation, spatial information in general. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observation, and also just sharing and this common passion that we have. This is the current board of directors. Sherry is our president, Charles vice president, Charm is editor-in-chief, Mustafa at social media is the social media administrator, and Sana web administrator. As you can see, they represent a big part of the world. And then there's us. We are the mentees of a program started in December 2020 that aims to continue this student consortium in the next term with the new board of directors and I'm part of this with Lakshmi, Nimisha, Sunni, Hasharan, and Yogender. We are basically in this mentorship program to be trained to continue this the students consortium at the best as we can. One of the main things that we do at the ISPRS Student Consortium is we have our own newsletter, where is the main publication of the consortium. So far, we published 17 Spectrum edition, but before this rebranding, there are already online. You can find many other older versions of the newsletter. And the most recent issue is about just spatial information for sustainable development. And there is another one coming very shortly, probably by the end of November or early December maximum, and it's going to be about remote sensing of coastal environments. If you like it, stay tuned and check our updates. We also organize summer schools to help foster the geospatial information science to a broader audience all over the world. And the one that is currently active online now is in collaboration with IEEE GRSS, and is in Brazil. It's a Brazil chapter. It's still going. It started in August the 12th and is going until December the 16th. Find the details online. It is very interesting and a lot of very good lectures. Other things that we organize are social events like the virtual rooms were basically meetups for people during the first lockdown to gather and share some lectures. There were invited people from the White Elephant Club, for example, from ISPRS, very, very knowledgeable people that gave us lectures about topics on how to write a thesis, for example, another interesting themes. And also, of course, we organize webinar series like this meeting that we have today. An important things to remember: the next Congress, ISPRS Congress, is going to happen in Nice, in France, in 2022. Trying to be live, like in person, but also keeping a hybrid format. And I just wanted to note that there is an upcoming deadline for, if you're interested to submit your papers, and abstract and free papers deadline is the 10th of January 2022. And yes, basically now this is the webinar that we are about to start. Our presenter is Professor Jan Wegner. He's the head of the Ecovision Lab at ETH of Zurich. He's also associate professor at the Institute for Computational Science at the University of Zurich. He got his PhD in 2011 by Leibniz Universität Hannover, and then followed a postdoc and senior scientist position at the Photogrammetry and Remote Sensing Group at the ETH of Zurich. He was selected by the World Economic Forum in 2020 as one of the top 25 best researchers worldwide below 40 years old. He's the Vice President of ISPRS Technical Commission 2 and Chair of the Technical Commission 2 Working Group 6, which is large-scale machine learning for geospatial data analysis. That's what he's going to talk about. He is the author of many contributions, and I found Google Scholar more than 100 contributions, but I'm sure that there may be many more. And there are some guidelines before we start. The presentation will last around 40 minutes. Then it's going to be followed by a question and answer section of 20 minutes, and then closing remarks. Please introduce yourself in the chat box. Tell us where you're from, your name, and after this presentation, we'll be circulating evaluation form, and any feedback will be highly appreciated. And that was it from me, very quick. I could now leave the floor to our guest lecturer, Professor Wegner. The audience is yours, please. Thank you.
Thanks a lot for the kind introduction, Nick. Let me just share my screen. All right. So thank you so much for inviting me. It's a great pleasure to be here virtually with all of you and talk about recent research in the Ecovision Lab, and everything that I will present is joint work with Konrad Schindler from the Photogrammetry Remote Sensing Group at ETH Zurich, and Nico Lang, PhD student, and partially also Andres Rodriguez, another PhD. So while we are all still washing our hands, and at least in Central Europe, in the German-speaking countries, we're hitting the fourth wave with a lot of force at the moment. There will be other bigger challenges from my perspective coming afterwards, and we should not lose focus on what will change our lives and needs a lot of action right now in the mid and long term, which are climate change and biodiversity. And today I will present a topic in the way that our community in remote sensing, combined with a lot of data science, can help to mitigate climate change and also monitor and learn more about the biodiversity reduction. So what are we doing? So specifically, our goal is that we come up with a solution to produce a dense 10-meter ground sampling distant model at global scale for vegetation parameters. That is frequently updated. So every couple of months, you want something new. And we want to monitor the vegetations and have accurate parameters like biomass, canopy height, all of that, which are essential input variables to biodiversity models, and also to learn about carbon stock and carbon sinks and so on, that are essential to model the change of our climate. And the idea here is that I would want to advocate for is to use individual satellite images to predict such parameters. So, and this is in contrast to photogrammetric approaches where you would use stereo vision or multi-view stereo approaches to learn something about the three-dimensional structure of, let's say, the canopy, the forest, or the globe. So then I have structured this talk into 3 different parts. Some of you who have listened to another talk of me half a year ago might be familiar with the first 2, but the third is definitely new. So if we want to have a global solution, there are 3 different steps. And the first one that I will explain is how to use these individual satellite images to regress the canopy top height from individual Sentinel-2 multispectral satellite images. Then the second part is how we can come up with a global reference data set that we need for supervised machine learning, the way we are doing it, to come up really with a global 10-meter ground sampling distance model and map for all these different variables that we want to estimate. And then the third part is how do we combine the 2 first parts? So this dense 10-meter regression of variables and this reference data set, which is sparse at global scale from the JEDI LiDAR canopy, to then really have a global 10-meter map of a lot of different variables. And last but not least, I will show a cool application, how that can be very helpful for sustainable supply chains in the palm oil sector, for example, also cocoa sector. So let's start with the first part. So the idea is to think of the canopy top height prediction as a so-called monocular depth problem, inspired by computer vision or robotics or autonomous driving, which is that basically you have just a single image, and for each pixel in the image, you estimate the depth. And depth in our case is not depth in the general term, but it's canopy height. So for each and every pixel, we want to estimate the canopy top height, so the maximum height of the canopy of the forest or the vegetation, so to speak, in our case. And the overall workflow is rather simple. So what you want to do is that you take the Sentinel-2 image with its 13 spectral bands as input, you pass it through deep neural network, and as output, you get the canopy top height here. And color, also in the following slides for the canopy top height, is always encodes the height. So everything dark is very low and everything bright yellowish is very high trees. And I always give the references to the articles where this has been published already at the bottom of the slides for all 3 packages. So then something important for those people who are with 1 foot in vision and 1 foot in remote sensing is that for this, I would say, medium resolution images, you have to be careful to not directly use existing bottleneck architectures from the deep learning community for this resolution of satellite imagery, because you lose a lot of spatial resolution. So what we do is we avoid any down or up sampling. So basically we don't have a bottleneck architecture. We don't have this typical encoder decoder architecture that compresses everything in the middle. But we have one individual stream. We have stride one no-max pooling, so that's a bit technical for those who are not used to that. It's basically saying those are the parts in the network that are standard in vision, but we don't do it here because we want to avoid the spatial downsampling. And then we have, well, 18 identical blocks. The number doesn't matter, can be more, can be a bit less. That's what worked best for us. I think the interesting part is here, the kind of convolutions that we use from François Chollet's work, a CVPR 2017 paper, which is interesting in our community because it's the so-called separable convolution, in the sense that we look at different dimensions of the data at different times in the network. So this is saying that we first do convolutions in the spatial domain on the sentinel tool. So we only look at texture first in the different channels. And then on the output activation maps, we then look in the orthogonal direction across the spectral information. And this worked well for us. And my hope is a bit in the future that this is also easing and facilitating the way to make these networks a bit more interpretable, especially in our case where both texture and spectral information is important. So this is a loss function that those people of you who are used to machine learning will find very common and easy. But for those who are new to that, I put it here to demystify it a bit. Yeah, because a lot of people, if they look at such an equation, think, so I will never understand, but I will show you now it's a very easy idea that is behind this. It's a so-called Euclidean loss function for a regression task, yeah, for the continuous height values. So we do regression in this case. So that's the first part. And the second part in red, that's the so-called L2 penalty term on the model parameters. Let's look at the first part first. So what this is doing is comparing the ground truth value of the canopy top height at a certain pixel I to the prediction of the model. So that's our convolutional neural network. It predicts a value for the canopy top height in the forward pass, and we compare it to the ground truth value at that particular pixel. We do this for all the pixels in the training data set, and we try to then minimize the discrepancy here. And of course, the model is based on the pixel intensities across the 13 channels. And then if we would just do that, we would get into overfitting immediately. So this is why we have this L2 regularizer. It's a penalty term that says basically the overall squared sum of the model parameters shouldn't go too big. And what that does is it reduces the chance of huge individual spikes of very few neurons that lead to overfitting them. So it tries to more or less keep all the parameters in the same range. So this avoids overfitting. So and then we test our approach on 2 countries where we have reference data. So one, unsurprisingly, is Switzerland, where I am based, where we have the canopy top height for the whole country. And we have 2 test regions here, one in the Valais Lac Le Mans region here, and one more in central Switzerland, including also Zurich and Lake Zurich and so on. Then another region is in West Africa, the country of Gabon, where we got a lot of data from the NASA ELVIS campaign. That is full waveform LiDAR data flown with an airplane here. And why Gabon? Gabon is of high interest for as a test site for forest parameters, because you have very large conservation sites, a lot of natural, beautiful rainforest with very high trees, so up to 60 meters high and even higher, and also very dense canopy, so up to 100% coverage of trees. So and if we apply our method, we test then the results. We train on a part of the data set. We have a validation data set where we tune the hyperparameters, and then we have a holdout test set where we test everything, and then we do cross-validation and so on, right? So what we are plotting here is for the country of Gabon, we plot the predicted values versus the ground truth. So the ground truth is here up to 60 meters high, on the x-axis, and on the y-axis we have the predicted heights of the canopy. In a perfect world, or in a perfect approach, everything would be on the diagonal directly. But of course we have errors. You see this here, and the more reddish is it, the more pixels we have. And overall, for the country here of Gabon, we do it for those 5 test areas. We get a mean absolute error of 4.3 meters. And we do the same for Switzerland. We don't have so high trees in Switzerland, up to 40 meters high. Most are lower, though, 20 meters, 25 maybe. And we see a similar behavior. We get a lower mean absolute error just because also we have lower trees, right? So a bit below 2 meters here. And then we analyze this a bit more in detail. So this is now a plot that looks at the different height intervals of the canopy top height. So 0 to 10 meters, and says, okay, what's the error there? For Gabon in green, for Switzerland in blue, then 10 to 20 meters, 20 to 30, and so on and so forth. And we see that in Switzerland, we get very high errors here, above 30 meters, which in general is not surprising, because you get higher errors relative to the tree height. But here we had a closer look and said, okay, where in Switzerland actually is that? And we found that this is mostly in the very high alpine regions, so above 2,000 meters, close to Arlich Glacier and so on. And we thought, oh, that cannot be, because in such high places, high altitude, we don't have so high trees. And we basically found that our reference data has a bug there. So then we went back to our colleagues, and it's being revised now. So we should actually be a bit better than this mean absolute error here if we have better reference data. So, and then for Gabon, we keep on plotting here for very high trees, but you have to keep several things in mind, right? So we have less and less training data. Even in Gabon, there's trees above 55 meters are very rare. So we have almost none in the training data set, also only very few in the test set. But what you also see is that at a certain canopy reflectance, the signal saturates. So we can no longer really distinguish 65 meter high trees from a 60 meter high tree or 55 meter high tree. There we start basically the guessing, right? So this is also something that we have to keep in mind if we think about how to further develop the method and so on. So some visualizations. So this is now the canopy top height encoded in color for the whole country of Gabon. So you see here, this is the delta of the Como River coming in here. And again, color is encoding the canopy top height. So very black is very low tree heights, and very bright yellowish is very high trees. And we zoom in here in this white box that is plotted here on the right side, and you see it's interesting because we have this beautiful mangrove trees here in the delta that are very high trees. And I haven't been to Gabon myself so far. I would love to go, but we had to talk to our colleagues and said, yes, it's actually true. You have the super high mangrove trees in the delta here, and it's amazing that it can be detected with such a, let's say, monocular depth method, if you would term it. So that's pretty cool, I think. But what you also see, of course, is a bit of white dots. What are the white dots? Those are not, let's say, super high trees, but this is missing data. Why missing data? Well, we are in the tropics. We are using optical imagery, and we have a lot of clouds. So this map is assembled by using 10 images for every pixel across the whole year, right? But even if we do that, for some places where we have the white pixels, we never see the ground. We always have clouds. So that's a general limitation to the method if we rely on optical data only. So Switzerland, lower trees, same color scaling up to 40 meter highs, but now the very yellow, very bright values indicate not 60 meters, but 40 meters. We zoom in here in the canton of Graubünden, and we see also very beautiful structure of the predictions and so on. And you see a lot of fine-grained things. And I think the major message here is not that we want to replace aerial LiDAR surveys or something like this, but our approach could be a complementary approach to update country scale and then global scale maps much more frequently at much lower cost. Because even in Switzerland, a very rich country, is the whole country is only flown every couple of years with the airplane, because otherwise it's just too expensive. But with the satellite images in our approach, you can do this every year and every half year even, and then look at the biomass changes and other changes. And that's even more important for other regions in the world where you have almost no aerial data at all, right? But there you would have the limitation of missing reference data. Now, in this next step, I will show you how we can scale globally to get better reference data, where we can then train our first part again and really have for a global scale for every place on the globe, have this 10-meter prediction and sampling of forest structure variables. So what we are doing here is that we turn to our NASA colleagues on the University of Maryland, so Ralph Tobaya and John Armstrong. This is joint work with them. And also on the computing side, our friend Peter Gahler, who is at Amazon Research, helped us out. And so this is what you see in the image here is the number of samples of the JEDI sensor, which is a full waveform spaceborne laser scanner mounted to the International Space Station. And let's have a look at how they explain it in the video. So this is a video I basically stole from the NASA and University of Maryland, which shows that this is a laser scanner with 8 beams mounted to the payload module of the International Space Station, which is continuously flying around the globe. And you have these 8 different tracks. And you also see you have a gap in between across the flight path. And you also have a long track. You have several 100-meter gaps between the individual footprints. And for those who hear about full waveform LiDAR for the first time, this has been around for quite some years now for aerial sensors, but for spaceborne sensors, it's still pretty new. And it's a fantastic sensor, I must say, because it creates a lot of potential and possibilities for analysis. So what it does is sends out a pulse, and the pulse then reaches the canopy here, and all the reflections of this pulse, so we have more than 1,000 that come back, are all recorded when they come back to the recording module of the LiDAR device on the ISS. So you get a long vector with more than 1,000 returns. And then you really see where a lot of signal happens. So there's a lot of signal coming back from the top of the canopy, so along the x-axis here. And then in the center here in the middle, there's a bit less, and then you get the ground peak again. And you can easily see that if there would be some bushes, you would get a lot more signal here as well. So you get a very nice analysis and a signal of the vertical structure of the forest and the vegetation in general. So that's a very rich signal. And for our case, for canopy top height, it's a simple task, basically. So what we want to do is estimate and measure the distance between the top peak at the top canopy to the ground return. So, and that gives you the so-called RH95 or RH98 in our case. So the top canopy height minus some outliers. And when we talk, we calibrate this now using a deep learning approach. There's also another approach done by UMD and NASA themselves that is more rule-based. But we wanted to have a learning-based approach, which turned out to be very efficient and quick. And for that, we need then ground truth and reference data. And we used the training validation test sites of our NASA colleagues. And here the dots indicate where that data was sampled with airborne LiDAR, and then ground samples to calibrate the LiDAR. And the size of the dots say how many samples were taken at those places. And that's not surprising that a lot of samples are where NASA comes from, so in the US, with southern Canada, then some in Great Britain. Then there is luckily quite some in the African tropical regions here. There is then a lot in Australia, and some, not too many though, unfortunately, on Borneo. And you also see with that we have a lot of missing, we have huge gaps. For example, China is missing completely, India is missing, and then also Central Asia and so on and so forth, of course. And also the whole South and Central America is missing too. So this is all something that shows that there's a strong need for collecting more reference data, but we had to live with what we had here. And just for your understanding how they basically work, is that this full waveform airborne LiDAR data sets, is where the dots are, is used now to simulate JEDI full waveforms. And then these simulated waveforms, they are matched to the real waveforms that are coming in by the flying sensor. Right? And then you say, okay, if I have the simulated matched to the real waveform, this is at the place of a simulated one, this is where I say the reference data ground truth is, because the problem is you don't know very exactly where the next LiDAR footprint will be. So it's hard to go in advance to a place and say, look, I only sample reference data here. This is why you have to do it the way they do it, to have a bit of slack. So this is just the distribution and the data analysis of the reference data that we have, that one should always do to be sure that you don't overfit to very particular settings, and then you take your model and it doesn't generalize it to new settings. So you see that concerning the canopy height, so the so-called RH98, so the 98th percentile of the canopy height, this is the distribution across all the reference sites. So you see we have a lot of data here, of course also a lot close to zero. We have almost no data between 40 and 60 meters, and this will become more important later. We have some different slope angles here as well. And then probably the most interesting part is the canopy cover here. And this is important because, of course, we have places without any forest, so there's zero coverage, but we have very high coverage, especially in the tropical regions in Africa, up to 100% canopy cover here. And then we also made sure that we have nice coverage of the different plant functional types. So we do not always look at the same kind of vegetation structure, but we have a variety of different ones. Let's now get to what I promised in the title, the deep ensembles. So this is how we calibrate this JEDI data. So just to remind you, so what we want to do is we want to estimate from the raw vector of 1,000 incoming returns. So this is shown here on the left. There's a plot. So it starts here. You have 1,000 returns with different intensity, which is shown here on the x-axis. You want to estimate the distance between the canopy top and the ground peak. So that's what we want. And we do not only want to estimate the height per footprint, but also basically estimate the uncertainty of that model prediction. And that's very important, right? Because you want to know how much can I trust the model prediction. And if you have worked with deep learning before, you might know that deep learning per se is not a probabilistic method. So you do get output scores, but they are poorly calibrated. They are either overconfident or underconfident. So between, let's say, 0.1 and then 0.9, there's nothing happening. It's either saying, I'm very confident something happening almost close to 1, or I'm very unconfident, but in between there's nothing. And this is something you need to change if you want to use it to filter your data and really learn about how good your model is at predicting in different circumstances. The way we do it is through these deep ensembles. So instead, we have 10 convolutional neural networks, all of the same architecture. It's 10 times the same thing, but we initialize them randomly. So all are differently initialized. And then instead of estimating just one output value per pixel, we always estimate the distribution and the Gaussian distribution here. And that means we estimate two values, the mean value of the distribution for the canopy top height for that particular pixel and the variance. Yeah. And then we minimize the Gaussian negative log likelihoods function. This is shown here at the bottom. That's the training loss that we use. And then we combine those. So what you get is that you get from each CNN, you get another Gaussian distribution, because it's a slightly different mean and a slightly different variance for each of them. So you have 10 different distributions predicted per pixel. And now what you do is you use some formula to basically approximate this mixture of Gaussians with another Gaussians. And you see it's not perfect, but at the moment it's sort of the most straightforward we can do. And these are ways, the strategy is something that has been employed in statistics, but a bit closer to our main domain in computer vision. So Alex Kendall and Jaren Gall, University of Oxford, they put forward some ideas and we got basically inspired by them how to do it here. So then you can estimate for this distribution, the variance, which is here. And this is then what you can use as an additional better calibrated uncertainty output per pixel. And then the question is, okay, how do you know if you calibrated your uncertainties well? Because, I mean, we have ground truth for canopy top height, but not for the uncertainties, of course. But if we think again, we actually do. So what we use as reference data is the empirical root mean square error, and everywhere where we have reference data. So we have the canopy top height, we have our model prediction, and the discrepancy, if we compute it over large area, gives you the root mean squared error. And our model predictions for this predictive standard deviation should now basically predict this root mean square error for our regression task. And if that would be perfect, we would again see this blue dotted line perfectly on the diagonal. And this plot takes a bit to think about how we do that. It's explained in detail in the paper. But what we do is we group sets here of standard deviation. And here on this side, we show this histogram is how many samples are in each standard deviation bin. And you see that the standard deviation that is predicted the most is between 2 and 3 meters here. And there it's rather well calibrated, right? And then you go off and you see for the very high standard deviations here, though this is usually for very high trees, also the calibration becomes less good. And this is also because we just have only very few samples there. So and if we then, now we can do something valuable with it, because we can say, look, the JEDI sensor is flying around the globe continuously. Yeah. So if I now calibrate my data and I predict, now here, this is a map of the canopy height, canopy top height, using our model at global scale. Everything high is very yellow, everything low is very blue. And we can now say, well, we only take 70% recall, those 70% most certain values. So we throw away the 30% most uncertain values, where we simply don't trust our model predictions. And I wait until the JEDI sensor comes back again, and then I try again. And if it still doesn't work, maybe I have to go and sample more ground truth in such situations, right? And this is, if we do that, if we have the 70% recall, so we throw away the 30% most uncertain values, then we get a global root mean square error of 2.7 meters for our JEDI calibration. And you have to remember that this now shall become our reference data set to train our Sentinel-2 approach, right? So we really say, okay, maybe a couple million points are enough. We don't need 10 million, we need only 5 million, that's already way enough. But we need them to be as accurate as possible because it should be our reference data. So we want to have not too much, so to speak, label noise in the data. Yeah. Yes, and this is just a bit of further analysis here to show you how well the model, our prediction, generalizes, because that's always an important question that you should always ask when using machine learning, that you don't overfit, so you generalize to new unseen scenes. And we see that the slope almost has no influence. Here, this is plotted, the slope. The canopy cover, that was very surprising to us and very important, is even if we have up to 100% of canopy cover, we still get very well calibrated canopy height. So this is always showing the canopy height for those cases, the mean canopy height, and then the box plot for that. So of course we underestimate a bit for the very dense canopy, but still we are pretty good here. And also for any other cases, we don't see any true systematic bias. So this is exactly what we want to see. For example, if we train on Europe, Australia, Africa, and Asia, and then predict on the US, that's fine. Doesn't matter so much. So we also generalize across continents and different biomes and so on, plant functional types. But so that was the good message. But now comes the drawback, and that's a general drawback of any machine learning method. That now, if we look at the residuals that are plotted here versus our canopy top height estimates, so this RH95. So here on the x-axis, we plot the canopy top height, and on the x-axis, we estimate we show the error. You see that we start to underestimate the tree height the higher the trees are, and that's a bias. It's a systematic error. And now you could say, oh well, we don't care, right? It's so rare, a high tree, but that's not true. Those are the most important places. And so we underestimate the high trees, but those high trees are overproportionately important because they contribute overproportionately more biomass. So if you really want to estimate your carbon stock, how much carbon is stored somewhere, you want to know, you don't want to underestimate those high trees, because there you should be very accurate. And why is this happening? Well, it's a standard issue in machine learning. If you look at the distribution here, the histogram of your training data, you see that they're here between 40, 60 meters, which corresponds to here in the plot, we have almost no training data. So if we have a global loss function, like I showed you, this negative log likelihood that tries to minimize the overall error, it tries to focus here, where most of the data points are, and doesn't pay so much attention to the very rare cases. It's fine for the loss function to also have very high errors there, as long as for the dominant part of the data set, the error gets very small. And that's a very common problem in any real world application outside those computer vision toy data sets. This data distribution, right? That you have a very long tail distribution. You have for some part of the data, a lot of samples, and for some very low. Okay, so those are the two first ones. Now I will show you how we can combine the two. So the dense canopy height regression, we did it on a regional or country scale. Now we expanded our reference data set to global scale for the canopy top height. And now we will combine the two approaches. And I cannot show you a global result because it's still computing in the cloud, but I can show you some regional results here. So what we want to do is that we use now our calibrated JEDI pulses as the reference data that we use for train, validate, test, to then densely predict at the 10-meter sampling rate the canopy top height. That's the output. And this is now the map that we did for a part of Southeast Asia, so Malaysia, Indonesia, and the Philippines. You see that other countries are missing. For example, Brunei is missing, and also Singapore is missing. It's just those countries that we wanted here. Colors encoded, again, black is very low, canopy top height, and white and bright is very high, canopy top height. And now I will show you a very cool application. So we go to the so-called high carbon stock approach. What is that? So the high carbon stock approach is the basic approach to monitor sustainable supply chains. For palm oil sourcing, which is a huge environmental issue, also economical issue in Southeast Asia, also for other commodities that are commonly sourced in the tropics like cocoa, but also soy and so on, beef. And this high carbon stock approach, which is mainly led by Greenpeace, defines what landscape to protect, which landscapes can be developed. So, and it says, does this depending on the carbon stock? So how much carbon is stored in the forest? And it says the more carbon is stored, the more valuable the forest, the more we should protect it. So everything above a certain threshold, so 35 tons per hectare carbon, everything left should be protected. And everything to the right side, so degraded lands, scrub and open land, that can be economically developed. And if there is a company who wants to expand a palm oil plantation, they have to provide a high carbon stock map of the area. And they have to show that they are not destroying valuable forest here to the left if they expand a plantation. And if that is not happening, then multinational companies like Barry Callebaut is a huge chocolate manufacturer, Nestle or Cargill, Unilever, and so on, they follow this approach in their no deforestation policies. And if the suppliers don't adhere to it, they no longer buy. And there's also new legislation coming into place in the European Union. I think the law was passed 2 days ago. In the US, it's already existing, that enforces this on a legal basis. The problem is coming up with maps, but here we are. This is now a high carbon stock map, and you can take your mobile phone, use the QR code, and then load the Google Earth Engine app and explore it and zoom in and out. So this is the so-called high carbon stock map that now is already open source and online, which is the very first one that is doing that at such a large scale, which is now distinguishing the landscape into areas that could possibly still be developed and others that should definitely be protected. For example, in the center of Borneo, everything yellowish, lightish green has so much carbon stored to it. Also here in Papua, for example, which is at the moment a big problem, a lot of deforestation happening there. And we also overlaid when we did our own oil palm layer for a big part of this. So this is missing in the Philippines. There we only have the coconut layer, but we have it palm oil layer in Indonesia and in Malaysia. And we also add the Copernicus land cover layer. So what can you do with it? So this is now sort of the 3 steps that we take. So input Sentinel-2 image of a certain area, and you can already see something is happening here, right? And this is a palm oil plantation. So we correctly classified this as palm oil plantation, overlaid it to the canopy top height. And now we use this canopy top height product as input to an ensemble of 5 CNNs to predict, to translate canopy top height to carbon stock. And we do this using reference data from Greg Esner's group, and that they sampled in the north of Borneo and Sabah region. So we train another ensemble of CNNs to translate canopy top height to carbon stock. And this is what you see here. Then now this is a very valuable information, because you see that this egg white is all oil palm. And you also see that this is very close to the yellow part. So there's a lot of high density forest, high carbon stock forest right next to it. So this is a high risk area. And big commodity sourcing companies like Nestle and so on, they would find this very interesting, because there's a high risk here that this oil palm plantation at some point, and you see it here already coming, will eat and destroy the forest here. So it's something to absolutely keep track of, have an eye on. Yeah. All right, so almost done. So what are the next steps? So maybe some of you have seen that NASA released a month or 2 months ago a new biomass product. So we no longer have only canopy height per footprint, but also biomass, which you can translate directly into carbon stock. So we can now use this directly and as reference data, for example, combined with Sentinel-2 images, or we still keep our sequential approach, which allows for a bit more flexibility, and just use this biomass product now to translate our canopy top height to biomass or carbon stock at global scale. Then we want to scale it really globally, at least in the tropics, and add more land cover layers. So we have, for example, we also have a cocoa map in Ghana and Ivory Coast, but we need to add additional layers that are important for high carbon stock maps in this case, like peatland and mangroves that have a lot of carbon stock and also biodiversity. And then just a bit of caution. I mean, what I showed you, this high carbon stock map for sustainable supply chain management, it's a so-called indicative map. So it's missing important information, for example, about indigenous land rights. So it could also be that maybe the carbon stock is rather low, but still it should be protected because there is some indigenous people living on that land and so on. So this is something we cannot see from space. This is additional sort of legal layers that have to be added on top to then be used as a product. We are currently also developing a rapid forest degradation alert system based on Sentinel-1. So once we have the high count stock map, we know what are the areas that should be protected, and we can look at where is that changing, where is forest degradation happening. For example, in the cocoa sector, where are people starting to chop down the bushes, the understory, the rainforest, to plant cocoa bushes. And then we are now fundraising basically for a much bigger team to start in summer next year to turn this into an actionable, publicly available tool, so at global scale, that all companies, NGOs, stakeholders, smallholder farmers look at the same map and know what areas are at risk and where we should really pay more attention to. And then, of course, on the research side, there's a lot of exciting stuff happening, right? So there's new sensors in space, like the biomass initiative from ESA, or the NISA initiative from NASA and the Indian Space Agency, and we can use all of it. Another cool thing that we can do is, now that we have trained our model, we can also use it for Landsat data, and then we can look back in time. So we can use canopy height and also high count stock maps for, let's say, at least 10, 15 years, as long as the Landsat configuration of the camera didn't change or is similar enough. Right? So we can basically track over time where and when, and possibly by whom, was parts of the tropics deforested in the past. So that's sort of nice to have the archive, because it's a documentation of what is happening on our Earth. And now we have the tool to investigate more closely what happened in the past. All right, so almost done. A slight warning before you get too euphoric. So with all this deep learning, even if the results are good, and I'm very happy about them, we may sometimes, or very often, not understand the causality. So, for example, in our case, the question is, what evidence does our deep learning approach really pick up in the multispectral Sentinel-2 image to predict the canopy height? At the moment, we have a hypothesis, but we cannot prove it. So the easiest explanation, and a bit boring explanation as well, is that it just looks at the distribution of the sun shadow on top of the canopy. This is a hypothesis that was also brought up by other people before, like the Matt Hansen's group, for example, but we cannot prove it. Right? So you have to invest more time into learning about what really is learned here. And then you probably have seen this. So this is the hype curve, and a lot of new technologies follows that. So there's, I would say, a year or two ago, in our field, we have been at this peak of inflated expectations in deep nets. So we thought, oh, everything is possible, right? And there's a lot of startups popping up, basically promising the world just with artificial intelligence. And then you come into this true of disillusionment. For example, autonomous driving, we are a bit there at the moment. We say, okay, it was all over claims. But I would say we as scientists in our community, at least in our field, looking at remote sensing, we are on the slope of enlightenment. And this is where we now get super productive, right? Because we can quietly work on something without all the attention and all the biases that are taken towards us from, let's say, the media. And there's a lot of exciting things you can do if you want to protect the environment, help mitigate climate change, and protect biodiversity. So I hope I could motivate you to look into deep nets to protect our planet. So last but not least, some exciting future thoughts. So I hope I could convince you that uncertainty estimation deep learning is important to do. Then the combination of machine learning, deep learning with physics-based modeling, I think is very, very exciting. At the moment, we have two worlds, right? We have top-down models, so we know all the physics or chemistry, biology, and we have a forward simulation based on the model assumption, and we have bottom-up, that's machine learning, data science. We make basically no assumption, maybe a bit of a regularizer on the loss, but much more, everything is completely data-driven. But we don't make use of all the expertise we have already, and we should combine that both worlds. And that's very tough to do. And then, of course, explainable AI to really see what is the model learning is important. All right, and then last but not least, I want to give credit to Nico. So while I'm presenting this work, of course, my team is actually doing the work. And this, what I present today, was done by Nico mainly. This is his PhD work. So I thank you so much for your attention, and looking forward to your questions.
Very good. Thank you. Thank you so much. Very interesting talk. Very fascinating. Especially also the last remarks on causality. Big question of artificial intelligence right now is why they do what they do. So we have a few questions. Let's start with, let me read. The first question, Professor Wagner, is from Sumi. Is asking, in Indonesia, Philippines, and other countries have trees greater than 50 meters, nearly 80 meters. Is there any limitation in the canopy height model generated?
Yes, absolutely. So I think for the JEDI reference data, of course, we underestimate, but since the full waveform is rather strong, I mean, we will still underestimate, but we will get some reasonable output nonetheless. We might also try to correct our bias a bit using more reference data. But for the dense map, the signal saturates. So everything, I would say, above 55 meters starts to be random guessing. So for the canopy height model, of course, then it gets inaccurate in those cases. For the application to protect the forest for the high carbon stock map, it's not a big issue because it's way above the threshold where things should be protected anyway. So if there's an error between high density forest and medium density forest, it's not such a big deal because it should be protected anyway. But for scientific analysis, it is. And there we just, one thing is sample much more reference data, ground truth data on the ground to train a more model, but also at some point using a multispectral sensor and individual views is just limited. You have to look to additional complementary initiatives like an L-band sensor, so radar signals. There's a interferometric SAR tomography also out there that in very long wavelength, the L-band and so on, will have bigger chances to pick up those very high trees, right? So I think that's a limitation of our method.
Great. I have a question. The next one is from Finn. Most of the palm oil plantations in the Philippines are in Palawan, but the indigenous people there are against this, so the government is reconsidering the program. Actually, it's a claim, not a question. We have another question is, can the canopy height model be generated for the trees which are covered under snow throughout the season using LiDAR?
So let me repeat the question. The question is if we can track seasonal changes of the trees?
Sumi is asking if we can generate canopy height models from regions covered in snow, basically, during
snow, sorry. Okay, so we didn't try it. We only took summer images. But in general, if it's under snow, it will be very difficult, right? I mean, already for the LiDAR to penetrate the snow, it will be almost impossible because it's a space-bound intensity. At some point, it's just limited. And then from the optical image, you just don't see the tree. So I think that's impossible. My answer would be wait for the snow to melt and do it in a different season again.
One question, maybe more, but I start with one. You use multispectral imagery from Sentinel-2. Do you notice any particular band that works best in generating results, or you just use all the bands all together?
So yes, I mean, most of the information comes from the, let's say, RGB and what's the first two infrared and near-infrared bands. So you basically, most of the evidence is in the first, let's say, 4 or 5 bands. And then the rest, if you want to say computational resources, a lot of that you wouldn't need. Also because they are lower spatial resolution, so that 30 meters and 60 meters and so on. So we had to interpolate and upsample them. So at some point, I mean, from our side, we want to squeeze out as much as accuracy as we can, right? Then it's great. But if you think about an application a bit and you want to save computational resources, you don't need all of them.
Okay, interesting. Thank you. And Paris is asking, any plans for ground validation of the carbon stock estimate? And then second question, for the other land cover types, is there any possibility that your future results would also be integrated with other global data sets, such as mangrove cover from the Global Mangrove Watch?
Yeah, so both times, very good questions. The first question, we do need much more reference data on the ground. And I am trying to convince a lot of people and also funding agencies and donors to come up with a much bigger concerted effort and ground truthing campaign, which also would open source all the reference data for carbon stock and biomass. At the moment, it's a lot of smaller, let's say, different research groups that all have a different data set, sampled in a different country at a different time, following a different protocol. For machine learning, that's very bad, because you have different protocols and it's very inhomogeneous data, right? So you need to agree on a common protocol how to sample, then agree on a scalable sampling strategy, at least in those focus areas in palm oil regions, cocoa, for example. And then you need to really make a push together to sample a lot of data and make it publicly available. Yeah, not keep it in-house or to some company or whatever. No, it should be public, such that all of us can collaborate and push science forward. So I'm working on this, and there's a lot of momentum now. Also following COP26, there's also bigger players in the game, Google, for example, USAID and so on, German Development Agency, GIZ, and so on. So I expect in the next year that there will be some bigger project coming in that domain. So then the second question, will it be integrated? So first and foremost, I mean, we will make everything publicly available at global scale. The canopy top height and other variables, we will probably update the map every 6 months, make it available. And we are in talks with different people. So Global Forest Watch, the World Resources Institute is one of them. Google Earth Engine, they are based here in Zurich, Noel Gorelick and so on. We're in talks with them. And we are just sort of making the maps, right? We are putting them out there and every platform can just use them. So Copernicus, Land Cavalet, if they want to, they will be on the Google Earth Engine. They can be on the Global Forest Watch. We will not put any license, any restrictions on there. So everyone can just use it. And at least Google Earth Engine and Global Forest Watch, after my discussion with them, they would be highly interested in hosting that. So then you can just combine it yourself in GIS systems and use it for your purposes. And we see actually some companies like map hubs, for example, using our high carbon stock maps already by overlaying it to their map of oil palm mills. So they see what oil palm mill is in an area in a 50 kilometer radius around, there is high carbon stock, because that's something one should watch again. So it's being used already now in a GIS setting.
Thank you. Another question. What other researches are carried out in your lab which uses terrestrial LiDAR system, mobile LiDAR, and drones for forestry? As Sunny is very interested in knowing about your lab.
Yeah, so we have a wide range of projects. This is just one stream, and I think it's fascinating, and this is why I'm promoting it and talking about it so much. And we try to also gather more people, make a bigger team. But of course, we have a lot more projects. So if you want to get an overview, look at the EcoVision Lab website. Look at my personal ETH website. On the usage set, there's not so much at the moment. And just as an overview, so we don't do terrestrial laser scanning for forests at the moment, but we use it for automated wireframe and cut model prediction. So what we do is we get the raw point cloud of some mechanical parts or some buildings or something. We use it as input, and this output of the deep net is the 3D CAD model, CAD model, or wireframe model directly. That's one thing. And I'm supervising other PhDs as a co-supervisor here at the University of Zurich who look into forests. So there's, for example, there's initiatives going on by colleagues at ETH and in Google to basically have mobile terrestrial laser scanners go into the forest and really use it to scale up the ground truthing efforts for biomass and other forest structure variables using these tools. There's also colleagues at University of Oxford who are using them, terrestrial laser scanners in forests. We look at biodiversity, so iNaturalist data sets, so crowdsourcing of biodiversity, combining it with remote sensing data, and then you have this long tail distribution again, few species sampled very often, most species and the most important ones rarely sampled. That's an issue. We are working on that. We also do things like much more basic down to the techniques of how deep learning works. Some recent CVPR papers that we just submitted. So I can just say what we do is basically looking at what are CNNs actually looking at. And we see they are overfitting to texture, to very local texture, like the good old MRFs or CRFs. And we want to force them to look at shape for objects, to generalize better and use less training data and so on. So we want to reduce the style bias. We look at domain adaptation problems. So it's rather broad, but the focus, while we do have computer vision, the data sets a bit as a playground, our real motivation comes from the environmental sector. So we always have a bit the two words, right? Computer vision is often a better playground to play with new methods because there's massive amounts of data sets. We don't have to spend so much time to prepare data, and reference data is readily available. And then we use the inspirational methods and apply them at much larger scale for environmental purposes. That's a bit the idea, but we always fine-tuning, of course.
Okay, thank you. Conscious of time, I think we have the last two questions. In forest, some canopies are just above the canopies of trees which are below them. Is it possible to get canopy models of the trees which are at a different level at the same location? So
you're talking about the second level of the foliage.
I think
there's
so.
Big trees and lower trees. No, I mean, we can. We look at, so in this particular one, we look at the top canopy height. But what we did do is that, that's a different paper under review at the moment, not in the tropics, but for the country of Norway. In Norway, it's another rich country who has a lot of beautiful airborne LiDAR data. And with our colleague Stefano Politi from Nibio in Oslo, we are looking at, can we also estimate other variables, not only canopy top height and biomass, but let's say the RH20. So this is about the vertical distribution of the biomass in the canopy and other variables using combination of Sentinel-1 and Sentinel-2. And we see that that works rather well. So we can actually do that if we have high quality reference data. So I can only say in the case of Norway, which is not so relevant for the tropics, obviously, but there it does work. And this is, of course, important then for biodiversity modeling and other things. And of course, a very exciting next step would be to take that Norway study, scale it up globally again. But it takes another 1 or 2 PhDs to do that.
It sounds like you're still in the hype phase of the technological discovery rather than light enlightenment. But anyway, last question by Sherry. Do you think that you will be able to make, this is a follow-up to your previous answer about validation protocols. So do you think that you'll be able to make use of existing forest carbon inventory data, given that sampling designs, also size and shape, differ in many countries? How does the sampling design affect the possible validation of your results?
So yes, I mean, we do make use of existing carbon inventory data already. The problem is just that it's sometimes outdated. At least what we got. We also negotiated with a lot of private companies in Southeast Asia. We also got data, and we found it to be of very poor quality. So it's something that we found. Yeah, so that's of course a bit political statement from my side. But if a plantation company of palm oil is giving a contract to someone to sample biomass on the ground with the idea in mind to expand the plantation, it's not surprising that a lot of the biomass is underestimated. Yeah? So we see a strong bias in that data, for example. And then for different protocols, they do matter. because it says, okay, very often the sampling is done more following the convenience of the ground truth people, so following a road or something, easy accessible sites, instead of really looking at those sites, let's say, that would be the most important to sample. So there's a lot of different issues there. Of course, we can't just take all data we want, put it in the machine, get some result. The question is then, do we understand what we are doing? So I would be very cautious with this. Now, being in this field for a couple of years and having, so I chased a lot of these data sets. They are also very hard to get, also among scientists, without other groups enforcing co-authorships, a lot of restrictions and whatever. I think we need a fresh start here and really have be on common ground, agree, and then have a very large campaign and make everything publicly available. And so in the sampling design, of course, does affect the results tremendously, because very often it's just sites being sampled that are, easy to access, or following then the rules that the local crew on the ground knows. And this is biasing our results. So it's something one has to think about, and it's an open question how to do that in a concerted and well-designed effort, where to sample ground truth. Not so much in my team, but in the NASA JEDI team. So Laura Duncanson, John Armstrong, Ralph Dubaya, and there's other players in the field that think about this a lot, how to make this, how to sample more efficiently and at the same time a more representative data set.
Fine. Thank you very much for your answers. I think we can finish here. We can end here the webinar. Thank you very much, Professor Wagner, for your contribution. Thank you for all the attendees and also Sharon and ISPRS, everything. Thank you so much. And nothing. Stay tuned for ISPRS Student Consortium updates and the upcoming events. Thank you again, Professor Wagner. Do you have any final remarks for our attendees or our students, or anything to say?
So I think I would want to motivate all of you who are still studying and everything. Look at data science from the side, from what you can do with it, what you can do for a healthy planet and in our society. So of course it's attractive to also think, oh, I can go to big tech companies and work for them. That's totally fine, of course. But I hope to motivate at least a small portion of you to invest your talent into protecting nature and helping society as a whole, right? So that's probably a message. And I think it will grow more and more important even in the future, although it's high in the news. Really implementing it, working on it, and helping and supporting from a scientific side, but also in industry and companies, this is only starting now. So you will also have bright job perspectives from my point of view, if you look into the direction of sustainability, how to apply data science, remote sensing to nature and so on.
Very true. Okay. Thank you very much again. Thank you, the audience. See you next time.
Thank you. Bye.
Bye-bye.